Hey everyone, welcome. Today, we're going to dig into a really key concept in engineering economy, the arithmetic gradient. This is going to be a super practical, step-by-step tutorial. So whether you're studying for an exam or working on a real-world project, this will get you up to speed.
So picture this, right? You get a new piece of equipment for a project. That first year, maintenance is probably pretty low. But then year 2 comes around and it costs a little more. Year 3, even more. This isn't your standard flat uniform series. It's a cash flow that's changing, it's growing. The big question is, how on earth do we analyze something like that?
All right, so here's the game plan for today. First, we'll nail down what an arithmetic gradient actually is. Then, and this is the most important part, we'll learn how to deconstruct the cash flow. After that, we'll jump into the math, solving for present worth and the annual series. And to wrap it all up, we'll look at the modern way to do it, with a spreadsheet. Okay, first things first. Let's really define what we're talking about here. What exactly is an arithmetic gradient? You know, the name actually gives it away. Arithmetic just means we're adding or subtracting the same amount each time. And gradient is that constant amount of change. We call it G. So all it is, really, is a predictable, straight line change year after year. Okay, now this is a super important detail, so pay close attention. It's all about the timing. The very first payment, the one in year 1, we treat that as our base amount. The actual change, that first G, doesn't even show up until the end of year 2. Getting this convention right is absolutely crucial for setting up these problems correctly. And that little detail about timing leads us right into what I think is the most important part of this entire explainer. The secret to cracking these problems isn't some crazy new formula. Nope, it's actually a really simple idea. So here it is, the big secret. We never try to solve a gradient problem all at once. Instead, we break it down. We split it into 2 much easier problems that we already know how to deal with. The first is a simple uniform series, and the second is what we call a pure gradient series. And this shows you exactly how it works. First, you pull out that base amount from year 1 and just pretend it's a constant payment, that's your A, that happens every single year. Then, you look at what's left over. And what's left is the pure gradient, which beautifully starts at 0 in year 1 and then just goes up by G every year after that. So because we've sliced the problem into these 2 manageable pieces, solving it becomes a piece of cake. You just find the present worth or the annual worth for each part on its own, and then you just add them together. The total is literally the sum of its parts. Simple as that. All right, let's put this theory into practice. We're going to walk through a real example. We'll start by using the old-school factor method to figure out the total present worth, basically what this whole stream of future payments is worth in today's money. So here's the problem we're working with. Imagine some road tax deposits. They start at $500,000, and they go up by $100,000 every single year for 10 years. The interest rate is 5%. Our mission? Find the total present worth, P.
Check out how perfectly our deconstruction method applies here. First, we tackle the base amount. We find its present worth, P sub A, using the good old P/A factor. Then we do the same for the gradient part, P sub G, but this time we use the P/G factor. We run the numbers for each, and then, you guessed it, we just add them up.
And boom, there's our number. The total present worth for this whole 10-year cash flow is just over $7 million. See, once you break it down, it's not so bad at all. Awesome. So we've got the present worth. But what if we wanted to know something different? What if we wanted to find the equivalent uniform annual series? In other words, what's the single, constant, boring payment we could make every year that would be equal to this whole complicated, changing cash flow? Well, the good news is the logic is exactly the same. The total annual series, A sub t, is just the base amount, which, hey, is already an annual amount, A, plus the annual equivalent of that gradient part, which we call A sub G. So let's do the math. The base amount, A, is easy. It's just that $500,000. For the gradient part, we grab our A/G factor from the tables. We multiply our gradient of $100,000 by that factor, and that gives us its annual equivalent. Then we just add that result to our base amount. And that gives us our final answer, $909,910. What this means is that making those increasing deposits every year is financially the exact same thing as making a steady, constant deposit of this amount every single year for all 10 years. Okay, so using the factors and tables is awesome for understanding the theory, for really getting what's going on under the hood. But let's be real, in the professional world, you're going to be using a spreadsheet. So let's look at the modern, much faster way to solve these things. The big difference here is how we approach it. With the factor method, we have to split it into two parts, the base and the gradient. A spreadsheet is way more powerful. It just looks at the total actual cash flow for each year and solves the whole thing at once. It's fast, it's accurate, and honestly, it's what you'll be using in your career. So how do you actually do it? It's really just two steps. First, in a column, you just list out the actual cash flow for every single year. No splitting, no thinking, just year 1, 500,000, year 2, 600,000, year 3, 700,000, and so on, all the way down. Okay, then you use the net present value function, or NPV. Now, there's a really important little quirk with how this function works in most spreadsheets. You give it the interest rate, and then you select the range of cash flows, but you start from the cash flow in year 1, not year 0. The NPV function automatically assumes the first cell in your range is at the end of period 1. If you had a year 0 cost, you'd have to add it separately outside the NPV function. But for our problem here, it works perfectly. And getting the annual series? Oh, that's even easier. Once you have that present worth calculated in a cell from your NPV function, you just use the PMT function. You just point it to the interest rate, the number of years, and that present worth value you just found. Bam! It spits out the equivalent annual series instantly. So look, if you walk away with just one thing today, I want it to be this. Don't let an arithmetic gradient intimidate you. It's not some new, scary monster of a problem. It is just two very simple problems, a uniform series and a pure gradient series stuck together. Once you see it that way, you've pretty much mastered it. And that kind of leads to a final interesting question, right? We've spent all this time figuring out P or A when we already know G, but what if you flip it around? What if you have a target, say a present worth of exactly $200 million, and you need to figure out what that annual increase G has to be to hit that number? Now, that's the next level of thinking and a really great place for you to explore next.